Hello. In this video, we are going to discuss about one network solving tool, that is nodal analysis. Although our discussion will be confined here with DC circuits, but the concept is equally applicable for any AC network. Only the resistances are replaced by impedances and the source magnitudes becomes periodic, sinusoidal for the AC analysis. Nodal analysis is based on systematic application of KCL and Ohm's law. To discuss about nodal analysis, first we need to know what is a node. A node is a junction where two or more branches meets. So one of the node in the given network acts as a reference. The remaining nodes will have a fixed potential relative to that reference, which are known as non-reference nodes. The voltage of the node is considered, in case of nodal analysis, the voltage of the node is considered as the variable instead of elemental voltages. Now, if the voltage at each node is known, then any electrical parameter in the given circuit, which may be a voltage across element or current through or power consumption by any element, can be easily calculated. For a circuit having n nodes, n-1 non-reference nodes exists. Nodal analysis are classified based on the following three cases. Case 1 is a circuit without any voltage source. Case 2 is a voltage source connected between a reference node and a non-reference node. Whereas case 3 is the voltage source is connected between non-reference nodes only. So let us discuss them one by one. Case 1 is nodal analysis without any voltage source. So there are three steps to analyze such a circuit. Step 1 is to determine the number of nodes within the network. Select a reference node. Assign variable voltages, unknown variable voltages V1 to V2 up to Vn-1 as many voltages are applicable for the n-1 nodes. The voltages are referenced with respect to the reference node. Obviously, the reference node is taken at ground or zero potential. Step number 2, KCL is applied at each non-reference nodes. Now Ohm's law is used to express the branch currents in terms of node voltages. Step 3, okay. Step 3, this is the equation for Ohm's law, which clearly tells that the current flows from a higher potential to a lower potential through a resistance. And step number 3 is in step number 2 we have obtained certain number of equations. These simultaneous equations needed to be solved either algebraically or through Cramer's rule or any mathematical tool. As an example, we are going to calculate the node voltages in the given circuit. This is ground node, this one is node number 1 and this one is node number 2. So at node 1 we are going to apply KCL, where the second format or alternative statement of KCL is going to help us, which tells us that the summation of incoming current in a particular node is equal to the summation of outgoing currents. So applying that thing, if incoming currents are taken as negative, the outgoing currents will be taken as positive. So applying that at node 1, we get the equation number 1. In node 2, similar analysis tells that outgoing currents are taken as positive and incoming currents are taken as negative. So the equation 2 is given by applying KCL at node 2, and then with the application of Ohm's law, the nodal equation is transferred in terms of nodal voltages. So there are two equations and there are two nodes. Total 3 nodes are there. So n-1 means 2 simultaneous equations needed to be solved, which are given here. and solving yields the value of voltage at node 1 and node 2 are this 13.33 and 20 volt. This may be the home task for the observers. Next one is case 2 and 3. Case 2, when a voltage source is connected between the reference node and a non-reference node. So in that case, the voltage at the non-reference node is equal to the voltage of the voltage source directly, which can be evident from the figure given. Here in this case, this 10 volt source, this one, and this is connected between the reference node and non-reference node 1. So directly V1 equal to 10 volt. Case 3, if the voltage source, whether that is a dependent or independent, is connected between two non-reference nodes. So in this case, this node is known as generalized node or supernode. In case of a supernode, both KCL and KVL are needed to be applied to determine the node voltages. For a proper definition, the supernode is formed by enclosing a dependent source or independent voltage source connected between two non-reference nodes, and if any elements connected in parallel with this. In this case, the 4 ohm is not connected between node 2 and node 3. So this will not be considered into a supernode. However, if any element would have been existed in between V2 and V3 in parallel with the voltage source only, that would have been included in the supernode surface. So in case of a supernode, the voltage source inside the supernode provides a constant equation needed to solve for the node voltages. Supernode does not have any voltage of its own. And the supernode needed both KCL and KVL to be applied for solving it. So these circuits are based on case 2 and case 3 of nodal analysis. The user may try it. So let us take the example of this particular circuit given here. Node 2 and node 3 forms a supernode. Now in the supernode, let us apply the KCL. So we are getting this equation. In case of a supernode, the KCL is needed to be applied at the whole supernode surface. So that's why the total incoming current at the supernode equal to total outgoing current from the supernode, and this equation is obtained. So apart from that, in the supernode surface, application of the KVL gives the second equation, and that's why the circuit looks like here. And so the properties of the supernodes are: voltage source inside the supernode provides a constant equation needed to solve for the node voltages. A supernode has not have any voltage of its own, and it needed to be solved through application of both Kirchhoff's laws, that is KVL and KCL. This circuit is left as an exercise for the observers. Thank you.